Hi guys, can I get a sound check?
Sounds good.
Great. Thanks guys. Let's see. Okay guys, so first thing I was gonna do is go over the Project 3. So just a reminder that this is gonna replace midterm 2. So it's gonna have like a pretty big effect on your grades. So, so that's one. And it's gonna be due, what did I say? I think midnight on the 21st, which is the Friday of the finals week. Okay. So the entire project is on the logical effort that we just covered. So I like it because I think it like forces you guys to do a bunch of things, which I think are useful. So let's first talk about the setup. And these are like the important notes I have, so-called important notes here. So which are here. So the first thing is that each one of you is going to have, you know, I'm sure there'll be duplicates, or mathematically it's possible to have duplicates, but you'll have your own gate. Okay, so how many digits are student IDs? Is it like 10 digits or something? Anybody know?
8, if I counted correctly.
It's 8?
Yeah, I believe.
Okay, great. So let's say it's, I don't know.
9. I counted 9.
Yeah, if you count the front 0, it's 9.
So it's like
Yeah, my
0 something, blah, blah, blah.
Yeah, I was wondering if our first was 0, what do we do?
Yeah, it's technically 0.
Oh, really? Ah, so there's a 0, huh? 9, 8. So I should make this, I'll make this 0 through 5 then. So we weighted towards NAND. So basically it's the first digit from the left, meaning from here. Okay, so that'll tell you if you are you're doing a NAND or a NOR. Those are the two options. Second digit tells you how many inputs you'll have. So in this case, it's 3. So we've got a 2-input NAND gate. Okay, which looks like that. 1, 2, 3, 4, 5, 6, 7, 9, I don't know, whatever. Then basically I take the sum of all these guys, and divide it by 10. I have no idea what the sum of these is, and I'm too lazy to figure it out, but say the sum is, I don't know, 50. Okay, so basically you're gonna have to make the width of your NMOS be 5 microns, sorry. So this guy is gonna be, width is gonna be 5 micron and the length is gonna be 0.18, whoops, and this is a Chromium markup. Okay, so so the width is 5 micron and the length is 0.18 micron. Okay, and you would want to make this guy so twice that, so you'd make the width of that guy be 10 micron and the length be 0.18 micron. Right, that's for a, no, I'm sorry, I got that wrong. So if that's the case, you also want to make this guy 5 micron. That's because you'll have 2 transistors that are in series in a NAND. And so the resistance here of these 2 transistors is going to be the same as the resistance of a PMOS that's 5 microns wide. Does that make sense? So the sizing of a NAND gate, 2-input NAND gate.
So all the transistors are the same length and width.
You want to have this, you want to have the pull up and the pull down have the same resistance.
Gotcha.
So, you know, obviously if you have a 3-input, NAND gate will be different, NOR gate will be different. So this decides your NMOS input size. Okay, in microns, and then you have to do it PMOS gates, transistors, sorry, accordingly. And the lengths are minimum for both. Okay. So one thing that's happened, this is like one of my favorite projects. So I've had it in like a few different semesters. But so one thing that happens is, let's say you end up with, I don't know, you're like unfortunate enough to end up with a 4-input NOR, okay? With a 4-input NOR. Let's just forget about transistor sizes. A 4-input NOR is extremely slow. It's much, much, much slower than a 2-input NAND, okay? So when you do, there's a tendency, like when you get to these guys, we'll talk about this a little bit. So, you know, you have multiple stages. So let's say you have 4-input NOR. So I think you'd end up needing to ground these inputs, and then, you know, stuff coming in from the smaller size 4-input NOR, and you're driving a bigger size 4-input NOR. Anyway, this point ends up needing, it's just going to have a really slow rise time and fall time. And what people have done in the past where they've gone wrong is they've just had a really fast input in terms of the period of the input, so that the output at some point along the line, the output doesn't make a full transition to VDD. So the output will just kind of start doing this. So, you know, you'll get your output be swinging by, you know, a few hundred millivolts, or otherwise just not swinging full rail to rail. So it's a pretty easy solution. You just have to slow this guy down, the period, enough that you'll get your full rail to rail swing. So just make sure you do that. And if that doesn't work, means you got some other problem. So always make sure when you're doing this that you're getting full rail to rail swings. And as we saw in, I forget, it was a project 1 or project 2, if you're not getting the full rail swings when you go slow enough, there's probably something really wrong. I don't know what. Either you've got some labeling problems mixed up, or substrates are disconnected. Something's wrong. It has to go to rail. So anyway, make sure that, again, some of these can get really slow. Make sure you have the appropriate speed on your input transitions. Okay, so for everything, use the TSMC 0.18 micron simulation models. So I'm referencing section repeatedly, section 8.4.3 of Weston Harris, our book, as a reference, because he's taking you guys step by step through the same process, but I think he's using like a 65 nanometer sort of transistor model, etc. Don't use that. Don't just copy that over from the netlist, etc. But make sure you're using the 0.18 micron simulation models.
That's the one that you gave us for Project 1, right?
I'm sorry?
Those are the models that you gave us for Project 1?
Yes, those are the same models. By the way, I don't know if you can hear this snoring in the background. Sorry, but it's my bulldog, and she already kicked me out of my office because she was snoring there, and now I'm in the kitchen and she's following me around. So anyway, I hope you guys can't hear it, but if you do, sorry, I can't quite get away from her today. All right, so that's that. The other thing that's tripped people out in the past is these schematics. They have this X1, X2, X3, whatever, and it gets all confusing. You think, well, does this mean it's 6 times bigger than the unit inverter? It's not. It's just in SPICE subcircuit names start with X, and so it's X whatever, some number, So all it means is he's just calling this is inverter X1, this is inverter with the name X5, but the sizing is like this. So the NMOS is 128 times unit, and the PMOS is 256 times unit transistor size. So that's what I mean by this. It just gets confusing. Okay, so just ignore these X, which is their names. Okay, and then I think Logan asks for these. Do we want to use the models, or do we want to use the LT Spice inverter? So if I understood your questions correctly, Logan, you want to use the actual NMOS, PMOS transistors because you want to make sure it's picking the right SPICE models. Unless I don't think I've used the standard inverter out of LT Spice, so I don't know how it picks its transistor models and transistor sizes.
Yeah, it's probably just better to use the actual transistors then.
Yeah, I would just use an actual transistor. Okay, and then what I would do is I would notice repeatedly what these things are doing is they're like sizing things up. Okay, so I would try to use like M parameters and pass the M parameters as much as you can, so you don't have to like redraw, like you don't have to actually build 1, 2, 3, 4, 5 different inverters, but you can just pass M models, and I think you can do that. So hopefully that'll work for you guys. So those are the important notes. So the thing I think I heard here is that I should include 0. in your numbers. Okay, so the first part, so parts 2, steps 2, 3, and 4, what we were trying to do is to find, so everything we did in the delays, etc., was dependent on finally multiplying the numbers, whatever we got, by R sub n, R sub p, C sub n, C sub p. So these are drain source, and then C sub gate. Okay, these were giving our time constants for the actual delay. So these first steps, steps 2, 3, and 4, we are trying to get these parameters. So for example, what we're doing in this case, let's erase this stuff. So if you read the book, you'll see it'll sort of go through this step by step, but let me try to explain it to you guys. So what you're trying to do is, let's say this is the circuit that's trying to measure it's trying to create a certain, this step 2, okay, is to measure the gate capacitance, okay? So you want to know here, you're trying to figure out the gate capacitance. Let me erase this. What is it doing? You're trying to figure out the gate capacitance of this guy. Okay, so how do you do that? Well, the first thing you do is everything here and here is just creating a realistic input voltage swing and a realistic load. Okay, so what are we doing? So you can do crazy stuff here. You can say, I have my input voltage has a rise time of a picosecond and a fall time of a picosecond, etc. That's fine, from 0 to 1.8 volts. But as you go through this guy, and as you go through that guy, they'll impose their own rise and fall times and the pulse shapes on the pulse. So by the time you get here, you'll have a certain reasonable pulse shape and rise and fall times. Okay, so that's all these circuits are, these two first guys, that's all they're doing. They are giving you a realistic input to X3 and X6 here. Okay, and then furthermore, this guy, X5, is making a realistic load on this X4. Okay, the reason is if you don't put any loading here, this X4's transition could be extremely fast and it could give you an overly optimistic or pessimistic input gate voltage. Okay, so again, so these guys, let me just erase this. So again, these guys and this guy are just creating the right inputs and output boundary conditions. The real business end is these guys. Okay, so then what are we doing? Well, this guy is exactly the same as this guy, right? Same size device. X3 is exactly the same size device as X6. They're both giving the same, they're both getting the same input. Okay, so if this capacitor C delay, okay, if you size that such that, so let me try to draw, let's put in a time here and voltage. Let's say that this is what happens on node D. Okay, this guy. And let's say this is what happens on node G. So I picked a certain C delay. So I picked C delay being, I don't know, 50 femtofards, something like that. And I got this effect. Okay. What this tells me is that the capacitance of C delay, so the C delay, this transistor is the same device and has the same input as what's driving the node D. And so it tells me that C delay is larger than the gate capacitance of X4. Why? Because they're being driven essentially by the same inverters, the same sized inverter, the same input. So if there's a slower rise time on this node G, it means that this capacitance is larger than this input capacitance. Okay. And you basically start playing around with C delay. If you see this, you'll end up, you have to reduce the C delay, and then you'll gradually line the two up. And when you get sitting on top of each other, then this capacitance C delay is the same as the input capacitance of X4. So at overlap, at let's call I don't know what I want to call it, at complete overlap of node G and node D waveforms, C delay is equal to C gate of of X4. Okay, so you can kind of overdo this complete overlap because C delay is a perfect linear constant capacitor, and the gate the transistors, the gate capacitance of the transistors for NMOS and PMOS, as we'd seen in the transistor lectures, they're nonlinear. They'll change as the voltage in them changes. As this D makes the transition, your transistors turn on and off, those values are changing. So try to get them, as close as you can to each other overlapping, but you'll never get them exactly overlapped. But once they're reasonably overlapped, okay, now the C delay again is the same as the gate capacitance of this inverter. And let's say you had you said my unit, let's say our unit inverter NMOS size is the width is 0.3 micron. Okay, which I think it is for this device. So this guy, so X4 will have an NMOS of 0.3 micron times 32. And then the PMOS will have 0.3 micron times 64. So that's the total width of basically the gate width that node D has on it. Okay, so to get capacitance per micron of width, you basically divide the C delay by this total width, and you get a certain capacitance per unit width. And that's your C sub G. Okay. And then to make sure you're on the right ballpark, you can go to the table, again, it's in chapter 8. Look under the TSMC 0.18. It was a table that had, I think we looked at it once. It had all the, let me see if I can pull it up actually. I have it. Okay, so this table 8.5 is kind of your cheat sheet here. Okay, if you look at it here, this is the TSMC 180 nanometer process. And you're not, you're not going to get exactly these numbers, but here, if you look at C sub G, like this has 1.6 femtofarads per micron. If you're getting, 10 femtofarads per micron, you're sort of off the right path. But if you're at 2 or 2.2 or 1.4, I wouldn't sweat it. You're good. Okay, so that's good enough. You're never gonna get. The overlaps is only gonna be so good for what you got. Okay, but anyway, this is your cheat sheet. So you're trying to figure out this value for C sub gate. You're trying to get this value for. Whoops, why did that give me cross? So you want to get, let's see, you want to get C sub D for the NMOS. You want to get R sub N for the NMOS. And then you want to get C sub D for the PMOS. And you want to get R sub P for the PMOS. Okay, so those are the values we're trying to get in steps 2, 3, and 4. Okay. There we go. Okay. So here also, I'm suggesting that, let's see, did I say this? Yeah, I'm suggesting that you zero out these area drain, area source, perimeter drain, perimeter source for all your transistors, because strictly speaking, it'll still be okay. It's just additional loading on this node that might throw off your simulations, and you're just trying to isolate the gate capacitance. These guys set the drain and source capacitances. So I'm suggesting you set those to 0. Okay, just so that it's easier to isolate the gate capacitance. Okay, so that was gate capacitance. Now in step 3, you're trying to measure the drain capacitances. Okay, so same procedure, pretty much. You basically have, this is showing what happens in an NMOS case. You pick a certain device. I would make this more than minimum. Okay, I think, I don't know how big you want to make it. Maybe make it 10 micron wide, maybe make it 50 micron wide, just so that you're trying to, because if it's too, this is too small, you'll get too sharp of a transition here potentially. And it's easier to make a big mistake when you're trying to overlap this E value with the D value. If you got two things that are really making sharp transitions, it's easy to make a mistake rather than two things that are, in my experience anyway, two things that are slow in transition. Okay, so I would make this, and you're dividing down by the width anyway, so it doesn't matter, but so I would make it something, I don't know, 10 micron wide, 50, something like that, whatever. So for this, you do need to set the area of drain, area source values, because that's in fact what you're trying to measure here. Okay, so make sure you set that correctly. And again, I always make this mistake. Make sure especially the areas of the drains and sources should be like to the minus 12 value, because you're multiplying 2 micron sorts of units. So be careful about that. And then make sure make sure your NMOS is off. You've got the gate low and the source low. And anyway, you're doing the same thing. These two things are sort of creating the right, a realistic input here. And these two guys are exactly the same thing. And you're varying this, you're increasing and decreasing it to try to match the capacitance here. And this gives you C sub D for the N. Now, you have to do this twice, one for the NMOS and one for the PMOS. For the PMOS, you have to replace this with basically, you got to make your PMOS off. So I'll connect it like this and connect this point to D. Okay, and just make sure you got the substrates going there as well. Okay, so that's that. The resistance ends up being a little bit more tricky. So you kind of have to follow the derivation in the book. But so basically you have to do, thankfully it's only 2 inverters in that case. And you're doing basically you're varying H. You're doing one simulation for H equal to 3, one simulation for H equal to 4, and looking at the difference in prop delay for rising and falling to get the resistance of the N and the resistance of the P for those. Okay, again, the derivations are in the book. Okay, so with these activities, again, I would suggest that as you do that, you go back to your cheat sheet and make sure you're not too far away from your expected values. Okay, what's too far away? More than 100% away. If this is like 2.5 femtofarads, I don't care. If this is like 3 kilo ohms micron or 3.5 kilo ohm microns, doesn't matter. It's like you're only going to get stuff matching so well. Okay, so that's that. Next, so now we have all these numbers. What you could do with those numbers is, let me just jump to step 6, is you could, with those numbers, calculate the logical effort. You could create your table of H, which is the fan out, versus actual delay in nanoseconds or picoseconds or whatever, and you end up with some kind of a curve, right? You could do the hand calculation, which is the whole effort, the whole point of the logical effort. Okay, so that's step 6. You're doing stuff with hand calculation. So if you had a NAND, this slope would be 4/3 H, and then the P would be what, 2, I think, plus 2, and then you'd multiply that by 3 RC, which is, I've calculated the R's and C's from here. Okay, so that you'd actually get a table with various values of H and various values of delay for your circuit. If it was a 3-input NAND, it'd be a 5/3 and so on. So it's all the stuff that's in the table. Okay, so that's the hand calculation. And we're trying to compare that to what our simulation tool will actually give us. And so what we do is we actually set it up. This is for an example for a 2-input NAND gate. You want to make your NAND gate, you only want to drive one input of the gate after you, right? So you got to figure out what to do with your other input. The NAND gates, what you do is you hook up the other inputs to the supply. So you turn them all into ones, and then the input is, transitioning between 0 and 1. So effectively, you're hooking up the NAND gate as if it was an inverter. And these first two devices are just shaping the input. And then this guy is just sort of creating a reasonable load on the load. And you're trying to measure the delay on this device. Okay. And then you're going to plot that with different values of H. I've asked you for 4 different values of H. Okay, so this is just an example for the NAND. If you had, here's an example for the NOR. I believe for a NOR, you want to double check that, but I believe for a NOR, to hook it up to act like an inverter, you gotta, sorry guys, that's the Amazon guy delivering something. Not the barking, that's a dog barking, but anyway. Yeah, sorry. So anyhow, so basically you put your device there, you get your own from the simulation, you get a curve of different H values versus delay. And now it'll have its own slope and whatever. So you want to basically plot this guy and this guy on the same curve. I did that I just did it being lazy for a minimum size inverter. So I got some comparison between a simulated value and a calculated value. Okay. And, you could do it for, this is, the prop delay, strictly speaking, is average. If you want to be lazy, you could just do prop delay arising or prop delay falling. That's okay with me. If you guys want to just pick one so you do less work, that's okay too. So anyway, make sure you put in, give me a good report with schematics, waveforms. Make sure you give me the values that you got, 2, 3, 4. Anything else? Nope. I think those are all. That's my advice on this guy. So that's pretty much it. Do you guys have any questions at this point? Nope, no questions. Okay, well, if anything comes up, let me know. So that was the project. And now let's look at, we're gonna talk about our next topic, which is the wires interconnection between, let me make sure I have my notes up to make sure I'm gonna cover everything I need to cover. Oops. Okay, great. So far we've been talking about the transistors only. We've been talking about, let's say in the case of doing, the rise fall delay, right? We've just said, okay, we're only going to consider the input gate capacitance of this thing we're driving and the drain capacitances for what's driving it. And then we're only talking about the resistance of pulling up and pulling things down. Now it turns out that in a VLSI, in a chip design process, this interconnection wire actually has a significant resistance and capacitance of its own. And the reason for that is these wire layers, they're made out of layers. We looked at the CMOS process technology. Basically, first you create the transistors, and then you put dielectric layer, and then an interconnection layer, the dielectric layer, then interconnection layer. So if I was gonna do a cross-sectional drawing, this would be the silicon surface. I would have my transistors like that. The gate capacitance would stick out, and then I would have, well, let's see, have some contacts potentially going to drain source and to your gate. And then you would have some metal layers, metal one, something like that. And then you would have, you'd need some kind of a dielectric layer where that doesn't show up very well. Let's do pink. So this would be another oxide layer that you've deposited. Okay, and then you can put in another layer of metal, like metal 2, to do, I don't know, another set of connections, because you need to basically you need to connect different signals to each other, and you need to bring power and ground to all your circuits. So you basically build layer after layer. Next, you put in another layer of dielectric and, I don't know, another metal layer. Okay, and you build up your connections that way. So you have two issues that makes these interconnections be far from perfect, meaning that they have a significant amount of resistance and capacitance. The first issue is they are extremely thin. So, we're talking about, especially the lower metal lines might be, I don't know, 0.1 micrometer tall. So we're talking about an extremely thin metal line in terms of its thickness. So that means it can have a significant resistance to the line. And so the second thing is that they are these dielectrics in between, the metal layers, and between the metal layer and the substrate, which is grounded or at the supply, are also extremely thin. These inner metal dielectrics might be also 0.1 micron, and this might be, I don't know, a micron thick. And that leads to a relatively high capacitance, because you're talking about, if you look at them as parallel plate capacitors, the plates are very close to each other. So basically these lines connecting the transistors in a chip do tend to have a relative high resistance and capacitance. In addition to that, I think we talked about this, the vias and contacts also have their own resistance, but I think we're going to be talking primarily about wires today, okay, the interconnections, okay? And if you actually look at a chip under the microscope, I won't really recognize much. Let's say you look at it under an electron microscope. We talked about chips having billions of transistors. So that's what's, I got a 10 millimeter by 10 millimeter chip. Let's say it has 10 billion transistors. But, it turns out those transistors are actually extremely small individually. So if you look at the chip, what you'll see for the most part is the wiring. So the wiring is extremely busy because all this stuff's got to get, you can imagine how many interconnections you got to have between these billions of transistors, and they're overlapping. You have to route things, etc. You got to bring power and ground. So if you actually look at from the top of a chip down, you're really only going to see essentially interconnections. You won't see any transistors if you look at the top. So basically a chip is mostly made out of wires, and they're completely covering the top of the transistors. And they affect speed, power, and noise. The speed, you know, we kind of talked about a little bit here. The speed is all about sort of RC delays. So the resistance matters of the wire, the capacitance matters, the amount of time it takes to charge up a wire and discharge it in addition to the gate of what you're driving. So that's affecting the speed. Power consumption, we saw that it's all about CV squared F times sort of an activity constant. But so if we add this capacitance of the wire to our load, you know, especially in some nodes like the clock, you know, the clock, imagine a clock signal is getting routed all over the chip. So the capacitance of that node tends to be large. So it'll affect the power consumption significantly. And then the noise, we'll see, it comes from capacitively coupling of lines to each other. Again, the dielectric between the metal lines is really thin, means you have a lot of coupling capacitance. And to get the most efficiency, to get the most number of lines getting routed in your chip, you tend to also get forced into making those lines very close to each other. That means you're going to get a lot of crosstalk. Now, I think we talked about this before, but to try to keep some control over how you route signals, almost always, you don't have to do this strictly speaking, but always, this is strongly suggested, is to make the alternating layers run perpendicular to each other. Okay, so that way, let's say if you have metal ones run horizontally and have metal twos run vertically, and have metal threes run horizontally, and metal fours vertically. If you don't do stuff like this, you're almost surely, like sooner than later, you're going to get into places where you're just not going to be able to route through, because lines, you know, you'll have metal two running both vertically and horizontally, and all of a sudden you get to like a dead end, then you're going to have lots of problems. Another thing that happens is you're almost never working on a chip by yourself. So you have to come to some agreement with the other designers to always route things a certain way. Otherwise, you know, they'll find out that they'll need to get some signal through your block to get to their block. And because you routed things in, or you put a certain metal layer horizontally in terms of vertically, you'll basically be completely blocking their path to get across. So anyway, so alternating layers run orthogonally. That's not part of the design rules, but extremely, extremely highly recommended. Okay, so here's an example of, you know, interestingly, of how the interconnects look like. And it's kind of a little bit unbelievable, like when you do cartoons of interconnects like I drew here, it, you know, looks like, hey, like the transistor is about, you know, this, you know, the sizing here is, this guy is, I don't know, like this width is wider than the width of these metal layers, etc. And that's because back in the day it used to be like that, and old people like me think this way. But in reality, the transistors, if you do a cross-sectional, so these are scanning electron microscope pictures of different chips and different processes. So this is 90 nanometer process. This is a 45 nanometer process. If you look at this, the transistors are really these itty bitty things at the bottom here. So like this is a contact to, so this looks to me like looks like a gate here, a drain and source here. And then you can see how the metal thicknesses are actually start getting much bigger than even the transistor width, especially when you go up to metal 6. So what's happening over time is that as the feature sizes are shrinking, that means they're allowing you to make the width of these lines narrower and narrower. It was getting to a point where the resistances were getting just out of control high. So they started allowing these devices to be thicker than their width. So the so-called aspect ratio is how tall a metal line or a feature is compared to its width. So the aspect ratios are going up, and you can see how extreme they are, say, in the case of this 45 nanometer process. If you look at this, I don't know, metal, where is it pretty obvious? This metal 7, say. You can see that's the height that you can have and versus the width. So metal is actually starting to look more like a rectangle and less like a rectangle like this and more like a rectangle like that. Okay, so those are some of the things you notice. So the transistors are actually at the very bottom, and this majority of this sort of space on the chip is interconnect. You'll see that people are always pushing to have a larger number of interconnect layers. So this 90 nanometer process has 6 layers of metal. The 45 nanometer process, 8 layers of metal. There's a limit to that because each one of these mask layers and each one of the processing layer costs something. So the designers are always pushing to have more number of metal layers, and the marketing people, project managers, management, the money people are always trying to get you to use the fewest number of metal layers so that the part can cost less. Okay, so more metal layers in more advanced processes are very typical. High aspect ratios in more advanced processes are more typical. So the lines tend to be narrower and taller. And this, as we'll see, has some effects on your noise and capacitance values. The other thing that you'll see is that the lower level metals are thinner and can be spaced closer to each other. And the higher layer metals tend to be thicker. And so the design rules are forcing them to be further away. So typically what happens is you use these lower metal layers for, let me write this down for, make sure, see I got my notes on so I don't forget. Let's see, I have it. Sorry guys, I want to make sure I'm covering all this stuff. Okay. So yeah, so these guys you tend to have for sort of what you'd call local interconnections, because they're dense. They tend to be dense routing, but means their feature sizes are narrow. You can cram a lot of these things there, but high capacitance resistance. Okay, so you want to use these for local interconnections, like, you know, if you've got your logic gates in a block, you want to connect them up together, that's good. So these further top layers, these guys, and I'm sort of really generalizing here, but, you know, I'm not saying always metal 5 through metal 8 is doing this, or always metal 1 to metal 4, but it's pretty typical. So these guys you use for power distribution, ground distribution, and global signals like clock getting distributed, because these guys, you know, you can't, by the time you get through here, just imagine like for every line you get through at metal 8, you can get, I don't know, like 20 lines in metal 1. So you don't get a lot of routing out of metal 8, but just it's extremely thick, and it's extremely far from the substrate, et cetera. So it has lower resistance, lower capacitance, et cetera. So that's just a general rule. These are power, ground, reference voltages if you have them, and global signals. And these tend to be local signals. Okay, so if we look at like a wiring model of a line, like to say take an aluminum line or something with, so this would be like, let's say if you have 2 lines running parallel to each other and over a ground plane, say. And I don't know if you guys have taken like RF or electromagnetic classes or whatever. So you have a bunch of things. You have the resistance of the lines. So you have the resistances of the individual lines. Then, you know, all these lines actually have inductance values. So you'd have some inductance in parallel with the line, and we actually have inductances between the lines, but it's not included here. You'll have some capacitance to ground. So you'll have some capacitance to this ground, which is represented by these guys. But then you also have some capacitance between the lines, like these guys. And then, you know, this is a line and going to another line that may be connected. So there's like you have resistance, inductance, and capacitance. Okay. So a lot of time, in fact, well, most of the time and most of the lines, you can really ignore the inductances on chip. The value of the inductances at the distances we're talking about, the frequencies we're talking about, the frequencies can be very fast. We're talking about, you know, 2 gigahertz, 5 gigahertz, et cetera. In some lines, you have to include the inductances, like maybe on the clocks, et cetera, if you're running your clocks that fast. But most of the lines, you can just ignore the inductances. Now, on some of the longer lines, and a lot of the longer lines, you will have to include the resistances. It'll start being significant once you get to, you know, millimeter to wire length. So it's not unusual to worry about the resistance, but always you have to worry about capacitances. And at the simplest level, people really only kind of worry about capacitance. If you're doing an all digital timing simulation, it's really only worrying about the capacitance. if you're doing a sort of hand simulation with back annotation of parasitics from your layout, then you're going to start, adding resistances, et cetera, to here, and almost never will you have inductances in your wire models. Okay, so now let's look at the sort of the characteristics of interconnect. So like I mentioned, so you have, again, 10 billion transistors, and you're going to have a bunch of interconnections in between. But in effect, the way you design a chip, if you just looked at a random, if you have random distribution of transistors and connections, nothing's ever going to work. Okay, so effectively what you do is you got to put this chip, design it with a certain hierarchy in mind, or else it's going to take you 1,000 years to put this chip together. So the way to look at this is a collection of different blocks. I don't know, ALUs, there'll be memories, SRAMs, there'll be external memory interfaces, there'll be interfaces to mobile displays. That depends on what this chip is. There'll be, high speed, let's say 10 gig interfaces and so on. There'll be different blocks. So most of the interconnections on your chip are going to be happening inside here. And you're going to try to have as few global signals between these things as possible, just to keep things straight, okay? So just from a reduction of design complexity, you're trying to have a hierarchical solution so that most of the connections are happening inside these blocks, and even more, inside small portions of this block. So if you look at a distribution, a histogram of the wire length versus the number of interconnects that have that length, and this is sort of a log scale. It's a log scale on the vertical axis too. You'll see that by far the most interconnects, most of the nodes in your chip, by far the most, this is log scale, are going to be very, very short. Okay, no matter which generation of device. These are all older chips, but I think even if you look at the chips now, it's just by nature of trying to keep, some order in the way you design and just not turn it into a total chaotic mess. It turns out that most of the connections end up being local. This also has the advantage that most of the connections don't have a lot of resistance capacitance, so it tends to reduce the excess power consumption, excess delays that you see with long connections, okay? Now, and then you end up with very few connections will turn out to be extremely long. For example, again, in this case, you might have 1, 2, maybe 10, I don't know, depends on how many clocks. You'll have clocks that need to go to all of these blocks or some of these blocks. You might have bus lines that are, all these or some of these blocks internally are accessing. So you'll have a certain number of global lines, but much fewer than the number of local interconnects. And there's a continuity, and you'll have different values. But again, notice this is a log scale, so that we're talking about majority of nodes have very small number of very short interconnections, which is a blessed thing. Which means that when you're designing a chip and you're worrying about the interconnect, you'll almost always end up worrying. Unfortunately, it still might be hundreds or thousands of lines, but at least it's something you can get your head around as opposed to like billions of lines or whatever. But like the clock is going to get 90% of your attention when it comes to, you know, worrying about resistance, capacitance, and crosstalk, etc. And then, you know, next there'll be some bus. That's, you know, an important bus running through your chip and is running very fast, etc. But there's a limited number of lines. It's just the nature of the interconnect. Okay, so let's now think about, let's see, what did I think we've talked about this, about the capacitance of the line. So I've talked about the concept of aspect ratio, which is thickness over the width of the line. And that in modern processes, in old processes, these lines tend to be more like rectangles like this running. Now, these days, they're more like rectangles like that running parallel to each other. And so, and the pitch, by the way, which is an important thing, I think we looked at this in some of the earlier homeworks, is basically sort of how fast is the wrong word, like how much can you replicate these lines. So you want to know, a lot of times what you're doing is you're running line after line next to each other, and you have a limited width that you're trying to run a lot of lines. So this pitch idea is minimum width, or the width that you're going to use for your line, plus the separation between the lines says how many lines you can fit across a certain width, a certain routing channel that you're allowed. Okay, so those are kind of interesting definitions. Talked about the layer stack. The narrower layer stacks are for inside of cells that tend to be high density, tend to be thin and narrow. As you get to thicker lines, you're going to use them for power, ground, and clock. Okay. And God, I don't know what to say about this. Okay, well, anyway, this is just sort of amusing. I don't know how far you guys are going to find this amusing, but no, I'm not going to even talk about this. Never mind. The water versus inductance, whatever. So, okay. Another thing. So, did we already do this? I saw. For some reason, I thought we looked at this in the semesters are trying to run into each other in my head. But if you have a long line, so excuse me if I've talked about this before, and you just model it, you calculate the resistance of this long line. Let's say, I don't know, whatever, you got a 10 millimeter line, and you calculate the total resistance of this line, and you calculate the total capacitance of this line, and you want to use that in your simulation as if you had an inverter, a resistance, and a capacitance. Okay, it's going to give you a very pessimistic value. So that's called a lumped model. And it'll give you a pessimistic delay estimate. Because the real wire line, if you imagine the real wire line, so you know you're pretending like it's just one R, one C, but a real wire line looks like a jillion like small resistance, capacitance, resistance, capacitance. It's basically distribution of resistance and capacitance evenly all across the line. I'm drawing it like these little things, but they're really like infinitesimally small resistance and capacitance pairs all across the line. And that's a more realistic model, but simplest model is just the lumped. You just add all the R's and add all the C's You just use one R and C. And that, it turns out it's too pessimistic of a number. It's not going to give you an accurate number. It'll be slower than an accurate number. But if you go to this extent and you have your 10 millimeter line and you're using 1,000 R's and 1,000 C's, is just computationally intense and just complicated. Because imagine if you're simulating that, your SPICE is running differential equations for each additional node here. So you want to limit the number of those nodes, plus doing a hand calculation is impossible. Now, it turns out that this so-called pi model gives you a very good estimate of the full extended model, distributed system model. And in fact, a 3-segment pi model gives you a very accurate estimate. So what does a 3-segment pi model means? Means, let's say you find that the total resistance and capacitance is R and total capacitance is C. Okay, so total R is, or let's call it R sub T, and total C is C sub T. So if you make a 3-segment model, and that means you have 3, and it's called a pi model, I assume, because somehow this looks like a pi. I guess it kind of does look like a pi. So you make this R total divided by 3. You make this C total divided by 6. You make this C total divided by 6. And you get 3 of these guys. Let me just copy it over. Let me move it. Yep. Yeah. Okay, and then you connect it up and you put right here and you put your load here. It turns out that this is, so 3 segments of this pi model ends up getting, it's within 3% of a completely distributed model. So it turns out, that's a real popular model for long interconnect, is to use several segments, 3 segments of this pi model. And it makes both simulation easier, reasonable. Now you got an additional, 1, 2 nodes that you have to, you've added to it, and you're within 3% of a very complex solution. In addition, we can use our old Elmore calculation. So if you assume, for example, that this guy has a resistance, let's say pull down resistance of R sub n, you basically start running the Elmore model. So the delay here is going to be, R sub n times CT over 6. So that's plus R sub n plus RT over 3 times CT over 3, because I've summed these two up. So you guys got to remember the Elmore model is this guy first times this, then this guy and this guy times that, and then this guy, and this guy times that. So next one we'll get Rn plus RT over 3 plus RT over 3 times CT over 3, etc. So we can use the Elmore model also to get a pretty quick hand calculation of this delay. Okay, so let me stop right there. So that was sort of like general topics on interconnect up to that point. And then next lecture, we're going to talk about actual, figuring out resistances and capacitances and things like that. Any questions? If not, I'll let you guys go. Okay, guys, have a good weekend.
Thank you,
Professor.
Have a good one.
Thanks, Professor.
Professor.
Thank you.
Thanks.
I was wondering if I could talk to you with no one here.
I'm pretty sure. You know what, Anthony? Why don't you just dial into the office hours thing? So I'll just close out this, and we'll both get on the office hours then.
Professor, you gonna, oh sorry, you're gonna have office hour this week, right? Or
Yeah, I'll have it. I'll probably have to make it a little bit later. So
Okay.
I'll probably start. I'm gonna check my schedule, but I'll probably start around 10 maybe.
and we can come in if we have like questions about the project, right?
Oh yeah, sure, definitely.
Okay, definitely. Thank you, Professor.
Yeah, sure.
Professor, the office hours is okay. I'll just hop into there then.
Yeah, I'll just hang up now, and we'll both get on there.
All right, perfect. Bye bye.
Sure. Bye.